The second situation that we are interested here in this chapter is the uniform circular motion. By definition, a particle in a uniform circular motion moves in a circular path with a constant speed. For example, if we look at this car moving in a circular path like this, and if the speed of the car is a constant, we say that the car moves under a uniform circular motion. Okay, so we have that the speed is a constant, okay, for uniform circular motion. Now, if we look at the position vector of the car or of any particle moving under the uniform circular motion, you can see that the position vector at position A and at position B for any two position A and B, the position vector will have a constant length. Okay, you can see that the position vector will have a constant length. And if we look at the velocity vector, this vector v, and if we look at the point A, at any point A and at any point B, you will see also that the velocity vector will have a constant length also, because the speed of the particle is a constant. So we have that the position vector has a constant length, the velocity vector has a constant length. And since the particle moves in a circular path, we must have that if we look at the velocity vector, we must have that the velocity vector is perpendicular to the position vector. That is, the vector r and vector v is always perpendicular at every point on the path. Okay. Now, if we look at the displacement when the particle moves from A to B, okay, this is the position vector at point A, and this is the position vector at point B. Here we use the center of the circle as the origin. Okay, this is the center of the circle, and we use it as the origin of our reference system, our coordinate system. Okay, so this is the displacement vector, and this is the position vector. The particle moves from A to B, the position vector change from Ri to Rf, and the angle between these two vectors, Ri and Rf, if it is equal to delta theta. Okay, now I will show you that if we measure the angle between the initial velocity and the final velocity, Okay, if we rewrite the initial velocity and the final velocity, initial velocity is the velocity at A and the final velocity is the velocity at B. We rewrite it here. We will have that the angle between VI and VF is also equal to delta theta. This can be easily proved as follows. We want to find the angle between VI and VF. So if we draw the line along the direction of VI and this the line along the direction of VF, so we want to see that this angle is equal to delta theta. Okay. Now, if I denote this angle as phi, and I denote this angle as a psi. Okay, and when we look at this triangle, this Ri, Rf, and the displacement delta r, you can see that this triangle has two sides with equal length. Ri and Rf have equal length. So we know that this angle is also phi. Okay, so we can write this is phi. Okay, and from this figure you can see that if we add phi, this angle is psi, not phi. Okay, this is psi and this psi, and you can see that if we add psi and phi, we will have that the angle psi plus the angle phi is equal to pi over 2. Okay, this is because if you look at this figure, this angle is pi over 2, and when you add this angle with the sine and phi, you must get the angle pi or 180 degrees. So we know that phi plus sine plus phi must equal to the pi over 2. Okay, again, if we look at this angle, we can see that this angle is also equal to phi. Okay, this angle is also equal to phi. It is because the angle between the position vector and the velocity vector is pi over 2. So if we add this sine with pi over 2 and with this angle, it must equal to pi. So again, we have that this angle sine plus this angle must equal to pi over 2. But we have that sine plus phi is equal to pi over 2. It means that this angle is phi. Okay, so you can see that This angle plus this angle must equal to this angle. So we have that this angle is equal to 3. Okay, so we can write that this 2phi is equal to pi minus 2 sine. Okay, now if we look again at this triangle, this triangle Ri, Rf and delta R, you can see that if we add this angle with this angle and with this angle, we must get the angle, the total angle inside a triangle must equal to pi. So we have that 2 sine plus delta theta is equal to pi, or we have that delta theta is equal to pi minus 2 sine. And you can see from this equation that 2 phi must equal to delta theta. Okay, it means that this angle 2 phi is equal to delta theta as we expect. So we have that if we draw the velocity vector Vi and Vf here, the angle between these two vectors is delta theta. Okay, and that proves what we expect.